Hey, welcome to our next installment with parametric equations. We're going to keep looking at some calculus there, but I've got some questions for you. Do you remember this work up the top here? This work is from the unit circle, goes back right to the preliminary stuff in specialist maths. And let's just review that. Remember, this was the expansion of trigonometry to go out to defining those trig functions on a circle. So we've got circular functions, if you like, and that increased the domain on which we could operate with sine and cosine and tangent. So just remembering that we said P was a point traveling around the unit circle, 1 unit radius, and it would have x coordinate cos theta, y coordinate sine theta, and there's our angle in there. So that works quite well with the SOHCAHTOA stuff. And I hope you remember that, because here, this was your first introduction, whether you knew it or not, to parametric equations, where we're talking about relating points on the Cartesian plane to another property of the system, another parameter involved there, which was theta, the angle traced out by the line or the radius from O to the travelling point B on the circumference of the circle, in a unit circle. This is very, very important up here. A 1 unit radius circle called a unit circle. So I wanted you to remember that, because that goes way back, and at the time when we were doing that, we probably didn't say that theta was a parameter, but it is, isn't it? And what are we going to do with it? Well, you say, Huddy, we've been doing some parametric equations and calculus, haven't done much calculus with the parametric equations yet. Did a little bit in the last section on Bezier curves, and here it is here. What's going on here? Well, look at what's going on here. We're saying we're still with the unit circle here, and we've got arc length traced out there. But what's this? d theta by dt and dl by dt. That means you're looking at a rate of change of theta with respect to the variable t and the arc length with respect to the variable t. It looks very much like we're returning to the value of, or the meaning of, the parameter t as time. And we did a bit of that with Bezier, didn't we? We said if you're travelling around the Bezier curve at a certain velocity, where that was represented by 1 unit per second, and t was in seconds. Okay, so that we could get a expression for dx by dt and dy by dt as motion around the Bezier curve, and t was between 0 and 1, of course, in that context. So we're returning to t having the meaning, t being the parameter here, having the meaning of time. So what are we going to do? We're going to look at how fast our angle at the centre is traced out, and how fast we're actually travelling around the circumference. Okay, so let's have a look at that and develop that a little now. So got a few screen clippings here from Hayes and Harris publications, so it'd be a good idea to get hold of their book there and have a look. So here we still have the same old unit circle. Just keep in mind that's arc length, and here's our angle in radians we'll be working with, and this is r is 1. It's a unit circle. So it's worth keeping in mind the measure of angle theta in radians is arc length over radius, or L over 1. In other words, in a unit circle, the measure of the angle at the centre equals the arc length, if this is in radians. Keep that in mind. That's going to be important now, that connection. The unit circle makes everything a lot simpler to look at. And then we're going to, in this presentation, expand upon that. So have a look. So here we go. As P moves anti-clockwise, so we always go this way around the unit circle, suppose it does so with a constant linear speed of 1 unit per second. So unit circle has 2 pi r as the units around the circumference, total distance travelled, and so it's going to do that in 2 pi seconds. So 2 pi units is the circumference around the unit circle, and it's going at 1 unit per second, so it's going to take 2 pi seconds. In other words, the point P in t seconds travels t radians. Okay, so t seconds it travels t radians. or 1 unit per second, 1 radian per second. So at any time t, we have the x coordinate of point P is cos t, and the y coordinate is sine t. Okay, so that all goes back to this idea, the relationship between the distance travelled around that arc and the angle in radians there, which is, of course, going to be equal in a radius equal 1 unit circle. All right, so that's it. We're starting to work up a little bit of an idea of motion around the circle in considering a time frame here, not just the x and y coordinates related to the parameter theta. Okay, so come on down and let's have a look at a summary of the things we can do here. Well, first of all, we could call the angle at which, or the angle traced out here, the rate at which that changes, as an angular velocity. If you've done any physics, you'll realise this is one way of describing the motion of point P. It's got an angular velocity, meaning it's got a rate of change of the angle traced out at the centre. That's that one. And we could say this is 1 radian per second. We just defined it as that. The linear speed is how fast you're actually changing that movement, that linear movement around the circumference per second. In other words, centimetres per second, metres per second. So you're looking at the rate of change of L actually travelling on this arc here. And that is 1 unit per second. And we've said that that is true because of the relationship in the unit circle between the measure of the angle and the arc length. Okay, the two are equal in a unit circle here. And we could put this down this way. The arc length is radius times the angle in radians, and radius is 1. Therefore, let's just rewrite this. We've got L equals theta, what we've been saying for some minutes now. So if you differentiate L, thinking that, yes, it is a hidden or implicit function in time, isn't it? You can see that as time goes by, L and theta both change. So it's appropriate to try to measure the rate of change of L with time. And if we did differentiate both sides of this, we would say the rate of change of the length equals the rate of change of the angle is 1 radian per second, or 1 unit per second, 1 centimetre per second. You can see the equality of these two in the unit circle, and that's one of the reasons why we use the unit circle. Sorry about that. So let's keep going and build this up a bit. So you can see we've got a few parameters here. We've got x and y as our usual variables on the Cartesian plane. We've got theta happening there, and then we've got t, the time, which we're going to use our calculus with to see things about speed and velocities and stuff. Okay, so let's have a look. What are we going to say? Well, P is the point X and Y, but probably better written to remind us that it's changing with time. So we're thinking now as P as a function X and Y, P having coordinates X and Y, both functions in time. Or you could say here, we have just said this is cos t, comma sine t. We're developing it, aren't we? Because we've said that in that time of 1 radian per second, we're going to have coordinates cos t and sine t. Okay, around that unit circle. So we're building it up a bit now, so try and stay with it. And so what we want to do here, have a look, we're saying we want to find the velocity vector. The velocity vector. So we want x prime t. Okay, the velocity vector would be the derivative of cos, and y prime t would be the derivative of sine. Uh-oh. Can you do that yet? You've done a bit of calculus in other subjects, the preliminary to this one. But can you find the derivative of x and y now that we've called it cos t and sine t? Can you do that? What we're going to do now is play a little game with just investigating it ourselves And then later on in this course we will prove what the derivative of sine and cos are. I want you to journey a little bit with me now in our endeavour to find the derivative of sine and cos in a Hutty's trichotomy for the derivative here. You have the derivative, and that means slope of the tangent to the curve, and it also means instantaneous rate of change here. Okay, now only one of we want the derivative because we want the velocity vector of that point P travelling around the unit circle. So what will we do? Well, we could use the slope of the tangent. In other words, the derivative of, let's do sine first, up here, the derivative of sine is said to be the slope of the tangent at the point, or the instantaneous rate of change. So is it possible to use the slope of the tangent on the curve of sine and try to find the values of that, and they would be the values of the derivative? Come on down and see if you can follow this now. So I've got here a couple of graphs. Well, one graph, sine x. And what we're going to do, watch this, this will be pi here. And this will be 2 pi. And this will be pi on 2. And 3 pi on 2. Okay, you should be very familiar with that graph. Now, if I'm looking for the derivative of sine, here it is down here, and I'm going to try and map it on here very roughly using the basic idea that the derivative of sine is equal to the slope of its tangent. So let's try and do it. When x is naught, the slope of the tangent, let's see if we can draw a tangent in, something like that. If we tried to measure the slope of that, y step would be 0.5 over x step. Now, the x step is in here somewhere. I shouldn't have put that there. It should be over here. Bit rough this is. So it's a bit less than one of these. Now, what's one of these? It's pi divided by 6, approximately 0.52 or something like that. So this looks like it's a little bit less than 0.52. Ooh, looks very close to 1, doesn't it? Okay, pretty rough. So down here, let's plot the derivative of sine x when x is naught is somewhere around 1. Let's now do this up here. Let's do the tangent at pi on 2 and come down here and plot it. The tangent at pi on 2 has a slope, oh, it's parallel to the x-axis. Slope is 0. Let's do a point in between here. What can we do? Let's do pi on 4, which is about here somewhere. And you could do this more accurately, of course. Pretty hard to write on the screen here. So I'm going to say my tangent there would be something like that. Can I actually find reasonably the slope of that? Could be a bit hard. Down here, let's say that point, 0.5, and through here, oh, getting rough now, 0.5, and what's the difference here? Y step is it's a bit more than 0.5, isn't it, going up there? I don't know, we could call it 0.52 or something. And along here, what have we got? Well, these are about, what are these? About 0.5 to, where are we? Somewhere here. You're very close. 0.5 to about, here. I would say probably about 0.6, something like that, 0.5 to and 0.6. What does that come to now? 0.52 over 0.6, approximately 5.6, approximately, I don't know, 0.7, something like that, 0.8, somewhere around 7.8. So let's put that in here, somewhere up here. Okay, so there's another point. And if we, let's come down to pi, that's a relatively easier one to look at. And it looks like there we've got the same thing again. It's about -1, isn't it? Okay, y step over x step, about -1 there. So here we've got that one and come down to this one. And then, where are we? 2 pi, let's take 3 pi on 2. 3 pi on 2 is another flattening for the tangent. So that would have a slope of 0. Oh, this is interesting. Look at this. Pretty rough, pretty rough. And you can look at Hayes and Harris because they've got a demo there. So this is about 1. What do you reckon? What do you reckon that graph is? Hey, that looks like cos x. Pretty rough stuff, but hey, that's interesting. I wonder if we can prove that later on when we do the actual calculus of the trig functions sine, cos and tan. All right, something to look forward to. Can we do cos now? So remember, what are we doing this for? We wanted to find the velocity vector, which was x prime t, y prime t, and that we said was cos of t, the derivative of that, sine of t, the derivative of that. So we've just found the sine of t's derivative. We reckon it could be cos x. Interesting result. You might try to do this more accurately than what I've done here and see how close you can get. Let's go down here to cos, because we need that. That's the x component. The derivative of cos is the x component of the velocity vector of that point. So here I've got the cos graph. Let's just put a couple of things in. Pi on 2, pi, 3 pi on 2, and 2 pi. Let's just do some key points now. What's the slope of the tangent to cos x, and therefore the derivative at x is 0? There's the tangent at x is 0. The slope is 0, so let's put it down here. Remember, this is the slope of the tangent at each point to the graph cos x. Let's remember that. Okay, as well as first principles, of course, we'll be doing that in the formal proof. And then at pi on 2, it looks like it might have a slope of about -1 again, so I'm cheating a bit here. -1 come down here. I'm not going to try and put one in between. At pi, so here's pi, the slope is 0. And then at 3 pi on 2, the slope looks like about +1. And this is only approximate, so it doesn't really matter. We're just trying to get an inkling of what's going on. And then at 2 pi, which is here, what's the slope? The slope is, it's a turning point, so the slope is 0, or the tangent's parallel to the x-axis. So it's there. So this one's graph, the derivative, looks something like this. Oh, that's interesting. That looks like something like neg sine x. Neg sine x. But the derivative, or the slopes of the tangent to the graph of cos x at various points, have the values neg sine x. Wow, that's an interesting relationship between sine and cos and their derivatives. Okay, so let's go on with that and see if we can do something with it. Now this is only conjecture now, isn't it? Very rough work here by using scale or trying to use scale drawings. One knows that's a big no-no in maths, but we did want to get some inkling of what the derivative of sine and cos might be, so we can have a look at the velocity vector of that point going around the unit circle. All right, let's come down and have a look at what we've got now. This is our conjecture. The derivative of sine is cos, and the derivative of cos is neg sine. Just remember, sine goes like this, and what we just did went like this. So I skipped that a bit, so I hope you could see that the one that we had was the neg sine graph. Okay, so that's our conjecture, and wait for later on when from first principles we'll prove that result. Okay, so let's have a look at a summary now. We've come along quite nicely. We've now said you've got a point moving around the unit circle, and we're going to bring in the parameter of time here, that as time changes it moves to a different point, and therefore it's got a velocity. So x of t is cos t and y of t is sine t, and this is going around the unit circle at 1 radian per second. And the velocity vector is, as usual, the x and y components are the derivatives, or the rate of change of the x component and the rate of change of the y component. And we are proposing that the velocity vector therefore is, remember this is derivative of cos first and the derivative of sine second, and that's our velocity vector. So, and there's an interesting result here. This is interesting. The derivative of the x component is negative y, and the derivative of the y component equals x. Well, that's fair enough. We said sine had its derivative of cos, so that's its derivative is exactly equal to cos, but the derivative of cos, here it is here, was minus sine. And this is the first time you've seen what's called a pair of differential equations. In other words, equations involving the derivative. Okay, some expression here saying the derivative is equal to something. Anything where you've got that is called a differential equation. Okay, so this is a very important idea later on, and it gets quite exciting as we look at various forms of the motion around the unit circle. So come down now and let's have a look. So we've got to check out a couple of things. Once again, the velocity vector is tangential to the curve. Now we expect that, don't we? Just let's review that. dy by dt equals dy by dx times dx by dt. That's the chain rule. Okay, the chain rule, where we're looking at the variation in one function with respect to a variable t, and how that is matched with, if you like, the variation in that function with respect to another variable times the variation of that with respect to the original t there. We had a look at that earlier. So let's rearrange this now. We said that dy by dx, therefore, this one is dy by dt divided by dx by dt. That's from the chain rule. So what's this really saying? This is saying the slope of the tangent to the curve is equal to, if you like, y prime t over x prime t. And what's that got to do with the velocity? Well, hang on. These are the components of the velocity vector. So the slope of that velocity vector would be its y step, which is velocity vector y prime t over x prime t. Okay, which therefore the slope of that tangent is this, and also the slope of the velocity vector is its y component over its x component. So we expect that. Let's test now the idea here by saying, all right, let's find OP. OP is that vector there. Now we're saying the velocity vector, this is our conjecture, was that. Does it work? Does it check out against the idea that the velocity vector should be tangential under that chain rule discussion to the curve? Oh, here we go. So we're saying velocity vector is derivative of cos t minus sine t, derivative of sine cos, and if we multiply that out, oh, it works. So this is a validation of our conjecture. It's not a proof yet that the derivative of sine is cos and the derivative of cos is minus sine or neg sine. But it is a nice validation that that velocity vector does have a dot product with OP of 0 and therefore would be perpendicular to it. Now what about the linear speed here? How fast the body's actually travelling? And so remember that's common to what we did with vectors before, the yacht problem if you remember, the size of the velocity is the square root, of the x component squared plus y component squared. And that would then be x component neg sine t all squared plus cos t squared, which would be sine squared plus cos squared, which is 1 unit per second. Which again has to be correct because our whole theory here has been derived on the idea that the point is moving at the rate of 1 radian per second or 1 unit per second along the arc length in a unit circle. All right, and we're going to change that a bit later on, and I want you to stay with it because we're laying some good foundations here, picking up some threads about the unit circle from earlier work and developing them into motion around the unit circle at various rates. So keep that in mind. Okay, so here we are. I've just flicked down to the exercises now. And so I want you to have a go at these. Show that all vectors perpendicular to AB have that form. Please notice all vectors. You can't just say prove that those two are perpendicular. Okay, I'll give you a hint. You've got to say let all vectors perpendicular be represented by xy or something like that. Okay, so all vectors perpendicular. We know that these two, when dotted, would give you a dot product of 0, but you might think about how to do that in general. You could also think about the idea that if you have a line segment, and this goes back to where complex numbers, I think, which is at right angles to another, then what do you notice about the coordinates here? Okay, that might help you. That's another way of discussing that. Maybe talk to your teacher about that later on. All right, so let's go to some variations about this motion around the circle. What if we did this, called the point P r cos t r sine t? What would that mean? Here we are. R would be the radius, wouldn't it? Okay, radius r. Just check that out, that you agree that that would mean that point would be r cos t r sine t. Now I want you to go through this exercise, and I'll talk about it a bit later on, but this is very, very important to build up the variations in movement around the unit circle that we could experience. Okay, particularly this one here, and I'll give you a hint here. I don't know whether you've ever gone roller skating or ice skating and have formed a whip where people chain up and go around and around faster and faster. That's what this is about. Only we're going to prove it mathematically there. So think about that one. Okay, so pause the presentation, have a go at those two. I'll show you the others and the fully worked solutions in a minute. Okay, here we go. Let's go down to question 3 and 4. You can see here we're playing around with the expression. I'm asking you to investigate what the effect of that thigh, that's the Greek letter thigh there, has on the motion. What's the difference here? And go through the whole lot, like has it affected the velocity of the body? What has that influence been? Okay, so pause and have a go at question 3. And just remember there are demos available from the disc accompanying the textbook. That helps you actually see it visually. Okay, so 4. Here's another one. Oh, we've changed something else in here. What's that going to change? You might have to look at what's the derivative of cos omega t. That's actually omega, not w. It's a Greek letter omega. And can you use differential calculus to have a look at what you expect here? This is important to unpack your knowledge here in part D. All right, have a go. And now I'll show you the last one, question 5. Consider the motion around the circle where, we've got lots of things happening. Look at all these changes. And I want you to see how those changes in our mathematical model, it is a model, isn't it? It's a formula describing a practical situation where we've got a moving body. So we're changing the model around, and want you to investigate and get up close and personal with why those changes will, or what effect they'll have on the motion of the body, and why mathematically that's going to happen, if you like. I keep getting rid of that. All right, so now let's have a look at the solutions. Okay, so here's question 1. Now I want you to stay with this right through to the end, because we have got a summary coming up at the end. Let's have a look at question 2. That's A, B, and C and D. And then I'll show you E and F. And let's go to 3. Let's see if we can get it all on here. Nope, 3, can't find it all on. So just go back a little bit there. So we've got 3A, B, C and D. And E and 4. And let's go to 5. Now we have 5. All right, I want you to stay with it now. So come down to the end and have a look at a summary again from Hayes and Harris. And we're trying to see the build-up here in the changes in our model, cos t and sin t. And we said the velocity vector had those components. Differential equations, oh, that's interesting. Simple idea though, a differential equation is something just explaining the relationship of the derivative to other parts of the system. For example, the derivative of x here equals minus the y. Okay, so that sort of idea. And if you put an r in front, what happens? Well, the derivative, that would be a constant, would stay out the front, there and there. So these differential equations would both have r in them, but they would be the same as the original line, be the same. What would be happening to the velocity though? What would be happening here compared to here? This is the whip idea of an ice skater or a roller skating being out on the long arm, and as they move around, the velocity of that body right out r further out will be greater. You can see it's r times both components. So think about that. That's a mathematical discussion of why somebody on the end of the whip is moving more quickly than the person at the centre. Okay, so I hope you can understand what I'm talking about. These are all people holding arms there. And so as we move through here, that angular velocity is the same, but the linear velocity quite clearly from this point is going to be greater. It's going to be r times. So to travel that angle, this person is travelling a greater L is greater here, out there, r times as great if you like. Okay, and then we put a thigh in, these thighs here. Did it change the velocity? Well, it changed the starting position, but the expressions here are still the same. And we would say, well, what's the effect of this thigh? It just starts at a different position. Okay, cos omega t, oh, better watch this one, because the derivative, when you differentiate cos, is minus sine, but you must multiply by the derivative of this function in here, mustn't you? Okay, remember that? Chain rule, function of function, or chain rule. So when you differentiate sine, derivative of sine is cos, but you must multiply by the derivative of the coefficient there. It's a function of a function. There are two functions there, sine of t and omega t. So, oh, what's happened now? What's happened? That's got omega times the original y component and the original x component. So it's going faster in the angular velocity sense here, and also faster in the linear sense around that curve. Just let's have a look at the idea here, and that is the differential equations would both have an omega in front now. So the if you think about that, the angle after time t is going to be omega t. So that's our theta. The angular velocity is d theta by dt, which is the derivative of omega t with respect to t, which is omega. So omega is going to be the radians per second there, because we put it as a coefficient of t. Fairly easy to understand. Theta now that you're finding the cos and sine of is omega times the value of the time that's gone by. So clearly it's omega radians per second for our rotational or angular velocity. And when you put them all together, here they are all together here, I hope you realise what would happen. It'd be at a different starting position for the thigh, and all the usual changes with the velocity expressions, and also the pair of differential equations would look slightly different. Okay, so we're going to come and do a lot with these pairs of differential equations. It's an interesting area where we change the relationship between x prime, y prime, or the derivative of x and y themselves, and look at how different forms of motion may result, not just a motion around the unit circle. All right, so I want you to really study this table because it's important for later on. But for now, that's all from me. So I hope you can get your head around this. You might have to go over it several times, talk to your classmates and also the teacher. But for now, it's cheers from me.